All right, welcome everyone. Today we're very happy to have Hank Lamm from Fermilab, and he's agreed to give us a couple of talks on subjects involving quantum simulation for high energy physics. And as usual, after the talk, we can take a short break and have a discussion for those who are interested. And with that, Hank, please take it away.
All right. Well, thank you very much for this invite and this opportunity to expound for about 2 hours when it's all said and done about this general idea that someday quantum computing is going to really change what we can do in high energy physics and the problems that we can hope to find solutions to. Here is sort of the outline of how I've broken things down for today and Wednesday. The idea is that sort of today we're going to talk about why we need quantum computers. So, how are they sort of at a fundamental level different than the computers we have today? And then there will be a long sort of section in the middle where we discuss what their current limitations are, what the future prospects look like and how long we should be expecting to wait. And, what is it that if you're going to be a theoretical physicist, do you really need to know to use them in the future? As opposed to, there's of course an infinite amount of information to learn about how quantum computers work at an experimental level, at a hardware level, at a software level, but sort of trying to key in on the important things that we would need to understand and appreciate. And then finally, we're going to spend, hopefully about 10 minutes discussing sort of the high energy physics problems that at least I personally am invested in working on and sort of how they fit into this whole landscape of problems that we can solve. And then Wednesday, we will get much more into the technical details about how, different parts of theoretical quantum field theory calculations are done and how they would have to be modified or changed entirely in order to be implemented on a real quantum computer. And then sort of what are the incremental steps that theory people need to be working on if we really want to make these machines useful to us on any time scale. So with that, the current state of the art of quantum computing can be very, very easily summarized as being just nasty, brutish, and short. This is the Google Sycamore chip, which was used a couple of years ago to, as they claim, demonstrate quantum advantage, which is this idea that they did a calculation that a quantum computer can do relatively quickly that a classical computer either cannot do quickly or cannot do sort of in the lifetime of the universe. And depending on who you are in the spectrum of people working with quantum computers, your threshold for calling something quantum advantage can differ very widely. So the particular example that Google showed was when they did their calculation, it was believed that in 3 minutes using their little quantum computer, they were capable of doing something that would have taken 10,000 years on a classical computer, where we're talking about not your laptop or a desktop, but the world's largest supercomputer at the time would have taken 10,000 years to come to the same result. And again, in this sort of area we live in at the moment of defining what things are really hard or what things really require quantum computers, within about a month or so after the Google result came out, people at IBM, who were the ones who designed Summit and also are deeply integrated in solving quantum computing problems, came out with a claim that no, in fact, this calculation you think would have taken 10,000 years on Summit can actually be done in something like 3 weeks if you're willing to devote all the resources you have. So this idea of quantum advantage is a bit, fluffy in terms of exactly when that claim will be considered unambiguously resolved, as we have a genuine demonstration of something on a quantum computer that's not doable on a classical one. But, because quantum computers are going to be, as I'll show, sort of dealing with quantum mechanical nature of physics as opposed to classical properties, it doesn't take much to grow from the current state of scaling to something larger, because typical problems, their difficulty on a classical computer is exponentially bad in the number of qubits you need or the number of bits that you're using to represent it. So going from this 53 qubit calculation to a 54 qubit calculation of the same thing would have been, a giant leap in terms of the computational resources. So you go from taking 3 weeks to something back in the range of years. So we're sort of in this transitional period where these machines are starting to be able to do problems that can't be done classically. Now, the problem is that these problems we're currently able to do on the quantum computer that can demonstrate quantum advantage are sort of designed to be problems difficult for a classical computer, but easy for a quantum one. But they're not designed to be an interesting problem. They're just something sort of by their nature designed to be difficult, to just demonstrate that difficult things can be done, not to actually solve a real interesting physics problem or chemistry problem, or even helping you out on the stock market. All of those things require much, much larger resources than just showing some specially designed problem that becomes intractable classically. So the current state is that we're able to do something with 53 qubits, and as I'm going to repeat over and over again during this talk, if you try and count like how much memory that is or how large it is, you should really think of a qubit as just a bit of information, which is where the name comes from. And on those 53 bits of information, you're able to do something like 20 machine level instructions. So if you want to run a program, it needs to be very, very, very restricted in its complexity if you want to be able to do anything right now. So what are the problems that we would like to solve? And sort of the broadest class of them that are probably of most interest to a lot of us in high energy physics are doing the real-time dynamics of quantum field theories. And these things, as I'm going to sort of show you, are inherently hard for a classical computer to actually solve efficiently for you. And so some of the specific problems that we sort of outlaid in this SNOMAS LOI that specifically would be of great interest to physicists and are almost certainly going to demand having a quantum computer to do are things like computing the scattering of nuclei with neutrinos that, here at Fermilab, we're deeply invested in learning how to do those theoretical predictions. So just determining cross sections of very, very large number of nucleons bound together in a nucleus and how they respond to being kicked by neutrino interactions is something that almost certainly will require a quantum computer because our classical ones will struggle with it. Something that I've personally been doing a little bit of work on is this idea that in the quark gluon plasma, if you want to understand its transport properties, like its viscosities and its hydrodynamic behavior, you sort of need to be able to do the real-time dynamics of this theory as opposed to just attempting to use classical lattice field theory calculations to extract these numbers. And then sort of the last one that I'm going to mention is this idea of hadron tomography. So if you want to learn what the actual physical distributions of quarks, gluons, angular momentum, charge, whatever those distributions are within a proton or the nucleus, in fact, these all sort of suggest that by their nature of being problems defined in Minkowski space, you really need a quantum computer to solve them. And sort of the idea that we were trying to motivate in this LOI is that while, as I just said, Google has sort of potentially demonstrated quantum advantage, it hasn't demonstrated what one might call practical quantum advantage, which is an idea that you're actually solving something that people really, really care about that isn't known already. And so sort of these and a few other topics are sort of discussed in this LOI about where are places that if you were giving me, an infinitely large, infinitely faithful quantum computer, I would be able to do a calculation that I have little expectation to be able to do classically, potentially in the lifetime of the universe. So, how is it that, before quantum computers, we actually, attack the high energy physics problems that we care about? And there's sort of, three broad ways you could try and, split this up. And the first one, is the one we're all certainly familiar with, which is just a pencil and paper. Maybe you add Mathematica to that nowadays, and you just say, I'm going to step by step work through, perturbative loop corrections, or I'm going to work through the diagonalization of something. And of course, I think at this point, we can all appreciate the limitations of that particular procedure. And so there was this big boom with classical computing to work on, numerical methods that allow us, much more flexibility in terms of the problems we can calculate, especially ones that are in, non-perturbative regimes where our standard sort of loop correction calculations aren't obviously going to be effective at getting results we care about. And so, with computers, we had this opportunity to use both sort of deterministic methods and Monte Carlo methods. And the class of problems those two things are well suited for can differ quite a bit. And the reasons that they sort of fail to solve the high energy physics problems that I was talking about that require the real-time dynamics are sort of subtly different, but they're sort of all inherently come from the same place. So let's talk about those two before we go into how the quantum computer actually works. So for deterministic methods, what you should imagine is something like, I have an incredibly large Hamiltonian, and I would like to diagonalize it, or I would like to time evolve with it and act on some wave function with this Hamiltonian. And the idea behind the deterministic methods are, for the same input that I give you, I will get the same output. And what these require is that in exchange for being deterministic, they essentially are exactly solving whatever problem you want, or to a reasonably high fidelity, going to precisely calculate the thing you want in the same way every time. And this puts up, relatively large barriers to doing these problems efficiently, because if as the Hamiltonian gets larger and larger and larger, for example, it becomes harder and harder and harder to do these exact diagonalizations or do these eigenvalue solves, or try and time evolve with something that's an increasingly large matrix that you need to multiply by a vector. And so all of those things typically will grow, with large polynomial scaling, if not exponential scaling, in the number of particles you want. And so realistically, when we're doing quantum field theory, we usually prefer the action, because we can sort of construct the path integral, and it's a more natural language because we're doing something that's fully relativistic and not breaking out space and time. But the Hamiltonian instead is this covariant object that, again, by being the generator of time, it doesn't sit in quite as nicely in this relativistic field theory framework as we would like. And from the point of view of doing deterministic methods, if you're doing a quantum field theory, this Hamiltonian is naively going to be an infinite by infinite size matrix. So it's as large as you can possibly imagine. And then you either have to start deciding how to truncate it sensibly or deal with this very, very large matrix. And so, for both the theoretical reasons that actions sort of sit nicer in our framework, and because they're sort of more numerically helpful for the methods that are successful, the high energy physics community gravitated very strongly towards the action formalism over the Hamiltonian. So, the method that we do use a lot more often in high energy physics, I would say, is the idea of using Monte Carlos. So as you try and do a larger and larger state space, you're trying to evaluate these integrals, you're trying to evaluate some matrix multiplication, and it just becomes prohibitively large. But at the same time, we have in our minds as physicists that while in principle the quantum field theory has an infinite state space, if we're only interested in the IR physics, we shouldn't really need that many of those states to actually contribute things sensibly. And so while formally the state space can be taken to infinity, we probably only need to sample a few states at the bottom. And so something like a stochastic sampling method like Monte Carlo might be very powerful for us. And this was in fact something appreciated long ago in the 50s, when people suggested that we could use classical computers to efficiently compute integrals, and where you're going to then sample from that integral with some probability distribution. And then when high energy physics developed into the path integral formulation, we all realized that, well, the path integral can just be written as a probability distribution, and therefore it nicely maps on to Monte Carlos. And to just briefly say this for those of you less familiar with the numerics of Monte Carlos, the idea is that you have some probability distribution that you want to sample over, or you have some region of space you want to do a contour integral around and figure out the area of. And at its very most basic level for a Monte Carlo, all you do is you propose some sort of bounding box that surrounds the region you definitely want, and you just start randomly pulling points out of that. And if it's inside the region you care about, you accept it, and if it's not, you reject it. And then the ratio of the accepted versus the rejected should give you the actual area of the inside box or bounded area, as long as you know the outside one. And so you can sort of, that's the most basic thing one does when we learn about Monte Carlo. And often, the canonical example is, instead of this very strange shape that I've put here, is to estimate the value of pi by putting a circle inside of it and sampling with respect to a square. And this entire method works really great, and we've had a lot of success with it in lattice field theory, but it does come with some issues. And just to say that, it's again instructive to sort of go to a more basic example even and talk about what is the practical solution that we get from this in sort of quantum field theory, and then how does it then fail us. And I'm going to recourse to imagining a bag where I'm going to have 2 blue balls and 5 red ones. And the question is, suppose I was going to ask you in sort of a quantum field theory language, what is the expectation value of the blueness of the bag? Which again, we're going to take as proxy, to be the number of the balls, the fraction of the balls that are blue. So what you would say is, well, really the expectation value of the blueness is equal to the integral of some blue operator acting over the probability distribution in the bag. And while this is formally some infinite integral that I need to do, where I would have to pull an infinite number of times to get the exact number, I know from sort of this idea of Monte Carlo sampling that the expectation value of the blueness is approximately going to be, for any finite number of pulls I take out of the bag, the blueness of each pull that I have. So you just take the sum of the number of times you pull a blue ball out divided by the total number of balls that you pulled out. And again, just to give you the really basic cartoon to make it clear when we're going to have things cause problems later, you pull 1 ball, you get no blue. So your current best guess for what the blueness is of the bag is 0%. And you keep pulling, and all of a sudden you pull a blue ball and you say, well, I've pulled 1 blue ball and 3 balls total. Therefore, I can estimate that the blueness of the bag is about 1/3. And you just keep pulling and pulling. And as you go to the infinite number of sampling limit, you will get the right answer. And what's important is that at any point along the way, you're also able to calculate the uncertainty, and you will be able to see that as you take more and more polls, the statistical fluctuations will decrease and your precision in terms of your confidence of what you've measured gets better. But there was this subtle assumption that we were making about this thing in order to make the Monte Carlo work, which was that this thing that we're calling P is really a probability that can be interpreted as some number between 0 and 1 in some sensible way. And this is not always the case. And in fact, if you think about normal quantum field theory in Minkowski space, the path integral, which we usually think of as some probability distribution, is not real valued. It is not bounded between 0 and 1. It is in fact generically not even real. It's typically a complex valued thing. So what happens if you try and sample things with a probability distribution that is not between 0 and 1? So let's again try and imagine a somewhat wishy-washy picture of how you could draw balls from a bag. So now we still have the 2 blue balls that we had. We still have the 5 red balls that we have, but we've now introduced this extra ball, which we're going to call anti-red. And this anti-red ball has the property of, it is whatever probability you ascribe to pulling a red ball, it is given a negative value with respect to that. So it sort of subtracts 1 red ball from the bag in general. And if we're thinking in like quantum field theory, you could imagine this being sort of a virtual particle that annihilates with another virtual particle to cancel out to an overall net charge of 0. So the way that we would try and make sense of this, once we've established that this thing does not have the correct probability distribution, it has the ability to be negative or to be complex, what we're going to do is assign to each draw an absolute value of its probability. And then we're going to take whatever relative sign or the complex value of it, so that sort of the imaginary piece, and we will just tuck that into the observable. So whereas before, we were measuring observable times probability, now we're going to be measuring both the observable and the relative sign that this particular ball should be given. And we're just going to normalize everything by the average value of the sign. And again, in principle, if you do this infinitely, you will get the right answer. So again, the procedure is you just start pulling balls out and everything goes like normal until you pull out that anti-red ball. And then what you do is you say, well, its expectation value is 0 because it has no blueness, but its sign is -1. And so you subtract from the bottom one integer, so 1 minus 1. And then in this way, as long as the number of these minus signed values or these imaginary values is small, you can just imagine that I would just run this forever anyways. And while sometimes I would get fluctuations that decrease, I can still eventually collide and get the right number that I was expecting out of the Monte Carlo. But there's this obvious problem looming over this strategy, which is, well, what happens if those cancellations are strong? What if instead of 1 red ball or 1 anti-red ball canceling out against 5 red balls, you had 1 anti-red and 1 red, so that basically you'd have a 50-50 shot when you pulled one out that you're going to cancel. So this is what, in the business of lattice field theory, we call the sign problem. It's this idea that when you're doing stochastic sampling, there are precise cancellations that are coming because you have things that would naively be negative probability distributions or imaginary probability distributions that you need to cancel those subtle, very, very precise matchings in order to get the correct answer out of it. And these are generically sort of just exponentially bad in the number of particles you try and put in, or if you're talking about a quantum field theory, the volume you try and do. So as you try and go towards the infinite volume limit, this problem becomes worse and worse and worse for you. And so if you think that my picture of the anti-red balls is contrived, I have an equally contrived but slightly different problem for you, which is this idea that, if I gave you, 2 Heaviside step functions and asked you to integrate them from -1 to 1 in both the x and the y direction. Now, of course, you can just do this by hand, and you would immediately tell me that the answer is that it's 0. But if you try and implement this integral in some sort of Monte Carlo sampling that's not clever enough to realize the structure of this integral you're doing, what will happen is it will take this just completely random path, and it will just start sampling either 1 or -1. And as you do it, every time the expectation value will be fluctuating wildly, because if you end up with too many on the plus side, you'll all of a sudden start diverging away from 0. And then you need to exactly cancel every one of those oddly distributed +1s by a -1. And so while you can see that if I sampled infinitely, I would eventually converge to zero. The convergence to zero, or the convergence to the right answer, will be much, much slower because there are very fine cancellations that have to happen as you go along. And there's no guarantee that you will evenly sample between 1 and -1 every time, which is the only way you would do it to get the right answer quickly. And you can sort of hopefully imagine to yourself that if I have some much more complicated distribution than just two Heaviside functions, that I don't know how to do it analytically, and tried to sample this thing, that this would be a real nightmare because I would have very, very slow convergence. And so sort of to conclude, these are the problems, both sign problems, I just called them. There is a related feature that can happen called signal to noise problems that really is coming from sort of the same fundamental physics problem. And these stymie our entire attempt to study lots and lots of interesting high energy physics problems, especially the ones in real time. So to finally put you into what maybe is a comforting level for theoretical physicists, the expectation value of an operator can be written in terms of the path integral, as we're all happy and used to. And in your mind, motivated by what I've been trying to tell you, you can imagine trying to decompose the action into the real part and the imaginary part, in which case you would have something that's real, positive, definite, weighted, and therefore you could use that as the sampling distribution. And then you might just take whatever the imaginary component of the action is and just throw that into the observable the same way that I did to do reweighting. And in the case where you have a purely real action, the average sign is 1 and everything is fine, and you can do a great amount of Monte Carloing. So for example, when we do Euclidean lattice field theory calculations, normally for like lattice QCD, most of the time there is no imaginary part of the action. It's a purely real valued number, in which case you can perfectly well do your Monte Carlo and you don't have any issues. Now, on the other hand, if you have some non-zero sign, all of a sudden, instead of some smooth, nice function where everything's above zero, you get these wildly oscillatory functions that go above and below zero, or they become imaginary themselves, or they become complex. And so you really need to get all of the subtle cancellations between the ups and the downs of this waveform to cancel precisely. Otherwise, you're going to be getting the wrong number. And getting all of those subtle cancellations between very large amplitude numbers is very, very difficult. And let me finish this last sentence and you can ask your question. Sure. And the fact of the matter is that if you think about what we do in normal Minkowski quantum field theory, there's almost never actually a real part to the action. It's almost entirely imaginary, in which case you have no good distribution to sample from, and it's a complete problem. Okay, go ahead with your question.
Is there any help to basically expanding around classical paths? So if I can at least know what sort of the classical possibly on-shell action is, and sort of h bar is small, and I think of quantum fluctuations around those classical paths, does that help smooth out this sort of problem?
Yes. If you had, as in my former life, I spent a lot of time doing this and thinking about this. If you have physical intuition about what the distribution looks like, or if you can do a semi-classical saddle point approximation, things like that can sometimes pull out some of the sign problem for you and reduce the problems that you have. There's a sort of an extension to this idea of the semi-classical saddle points by looking at what are called Lefschetz thimbles. And these, in fact, do have some nice properties that make sign problems better. But the problem with doing a saddle point approximation or doing any approximation like that is that if you're genuinely interested in non-perturbative physics, that truncation is not always as clear-cut or as safe as you might hope it is. And it can lead you to having systematic errors later in your observables you're trying to compute. So it is a trick that people use, and it is one of a large toolkit of ways we try and attack sign problems. And some of them are more rigorous in the sense that they have complete control over their errors, and some of them don't. But that is certainly something that is done.
Okay, great. Thanks so much.
Yeah. So really, the entire last 15 minutes of what I just said can be stated succinctly by, the wave function, the thing that we consider to be the probability distribution or the probability amplitude of a quantum mechanical system is inherently complex valued. And it was asking too much of that system to impose upon it that it's purely positive definite. And sort of that's the difference, is that classical distributions can be sampled classically with a Monte Carlo, but asking for a quantum distribution to be able to be sampled classically is asking too much, because it's asking to, inappropriately apply something. And, again, lattice field theory works, but it works because we go into Euclidean space where we're no longer dealing with quite the same complex valued probability amplitude. It can be rewritten in terms of a classical thermodynamic system, in which case the distribution is well-defined and is real and positive, definitely. So, phrasing it that way, it shouldn't be terribly hard to understand, well, what it would be that I gained by having a quantum computer in front of me. Because as I sort of said, a classical computer, what it does is it evolves things either classically, or it computes things classically, or it can sample from classical distributions. And a quantum computer, by its nature, as Feynman pointed out, by saying having quantum mechanics require complex valued probability amplitudes inherently makes it hard to do them classically. And this was his motivation for using quantum computers or having them someday, was that he didn't know how to do complex valued probability distributions efficiently. But what you gain is the fact that it's a quantum computer. It really should be imagined as you put in some quantum mechanical wave function and then you time evolve it. So a quantum computer is just a quantum system where you would, in principle, if we were talking about a digital quantum computer, have arbitrary control over that, how that system sort of evolves. And you can decide for it what it wants to do. And all you are then required is to take the qubits that go into this thing and map them onto the quantum field theory you care about. And all of this complex valued amplitudes is taken care of for you because you have it at your heart, a quantum mechanical system to begin with. And sort of to say that in the canonical words that people say, on a classical computer, all you have is bits. So all you have is zeros and ones that you build everything out of. And this doesn't allow you to efficiently tap into the fact that a single bit, if we were talking about quantum mechanics and talking about a qubit, does not just sit in either the 0 or the 1 state. It's allowed to sit in whatever superposition it wants with any complex valued amplitude for the 2 states. And it's genuinely a wider class of probability that is allowed on a quantum computer, because quantum mechanics allows a broader class of probabilities than classical computers in classical physics. So the punchline is that a quantum computer can efficiently represent this idea of having superpositions, and it also can efficiently deal with the fact that you're allowed to entangle states. And the reason that it is because it is at its heart a quantum mechanical system that you play around with. And while that's great, and of course that's what we want, it does not give you the quantum field theory. In the same way that if all I did was hand you a classical computer and told you you had to write everything in terms of bits, in terms of zeros and ones, you would not be able to immediately code up a quantum, any kind of classical simulator. So there's the work of mapping what we're given in terms of hardware and software onto the problems that we care about. But at least this system has the ability in some theoretical sense to solve the problems we want efficiently. So, what's on the market today? There's sort of 2 broad classes of quantum computers that people are interested in, and they're interested in them because the types of problems they're wanting to solve are somewhat different, and because also the hardware is easier to design in some sense for different types of problems. And doing problem-specific computing is maybe an interesting method as well, as opposed to having something like a universal quantum computer. But in terms of the digital quantum computers that are on the market, these ones are geared towards someday having a large-scale, fault-tolerant universal quantum computer that, regardless of what problem you would want to solve, if it is a problem that requires a quantum algorithm, it can be implemented on that computer. In the same way that we don't even talk about it today all that often about a classical computer that most of us have in our laptop is a universal classical computer. It can compute essentially anything we want. Whereas when we talk about sort of hardware specific or problem specific computing, this is a bit more niche these days in terms of theoretical physicists, but our experimental friends talk about especially designing an optimized piece of hardware that can do one calculation, which is the one they care about really, really, really well, but is not capable of actually doing arbitrary computation. And so here are the cute pictures of all these different systems. This is not, of course, everybody, but this is some of the big players that you might have heard of. There's, again, the Google Sycamore chip at the bottom left, and then to the right of it is the IBM machine, or one of the IBM machines, and they have this sort of interesting downward structure. So it's only really that bottom cylinder there that's sort of silverish, that's the actual computer. The entire rest of this is the control apparatus and cooling apparatus and things like that in order to make this machine work and to isolate it from thermal fluctuations and problems like that. Then continuing around counterclockwise, you have the IonQ and then the Honeywell machines, which are both used trapped ion systems and magnetic fields and lasers to deal with them, as opposed to the other two. And then the final machine, which is the Rigetti machine, which are built on using superconducting circuits as their sort of base qubit technology. And these are the ones that I'm most interested in personally. And these ones should, again, be thought of sort of in the direct analogy to a classical universal computer, where anything you want to compute can in principle be coded upon them if you're willing to put in the time to write the code. And sort of the other option available to us, and that, as I've put some references here, some high energy physicists are interested in, is the idea of an analog quantum computer. And sort of like the most famous one is D-Wave, and there are other ones that are similar that use different types of hardware as well. But their idea is that you basically have some system of a bunch of states, or a bunch of qubit or qubit-like things, but they're not actually going to be allowed to be arbitrarily controlled. You're going to sort of have some system with a partially tunable Hamiltonian. So you are allowed certain limited sets of interactions between these different particles, and you're going to be able to control this Hamiltonian. But you're not going to be able to sort of time evolve the Hamiltonian. What you're going to be able to do is just impose a Hamiltonian on how these particles all interact with each other, and you can somewhat control something like a temperature. And so what these problems are really, really useful for is trying to do optimization. If you're thinking about sort of general quantum algorithms that would allow you to do, traveling salesman problems, or trying to find the optimal minimum of a matrix, or finding the optimal parameter space for some particular problem. But also, by the analogy that I was giving you, these things sort of do annealing, where you have a fixed Hamiltonian that describes how the interactions work, and then you start trying to lower the temperature. And what this is useful for, that people have pointed out, was there are quantum mechanical and quantum field theory systems where it's very hard to find out the ground state of this system. And it's therefore also hard to find out what the ground state properties are. And that having a machine like this, that while limited in terms of what it can solve, there are problems in that scope that we might care about. And in particular, it's believed that trying to do finite density quantum field theory, so if you wanted to learn about the equation of state of QCD, an analog computer might be all you need. And what's important is that these analog computers are much, much larger. They have thousands or tens of thousands of qubits, but you're not allowed to do any operation you want on them. You're very limited. And if you cannot map the particular Hamiltonian you want onto the one that these machines are capable of doing, you're sort of out of luck. But people have worked very hard to show that there are interesting quantum field theory problems that can be mapped onto the available Hamiltonians. So this is an active field of research in terms of what can be done there. To hopefully scare you even more before I excite you at the end of the talk, today, we often, even as theoretical physicists, if we want to be involved in this space, we have to think in terms of very, very low level code. And I imagine some of you in the room are relatively decent programmers, almost certainly better than I am. So I have an actual couple of questions to see if anyone can recognize these things. Does anyone know what this code does? It's clearly written in a much, much lower level language than C or Python, or the thing that we would commonly as theorists use today. But can anyone tell me what this does? I will take that silence to mean no. And this is actually sort of assembly level code. So this is even obscured a little bit from what you really do on the classical computer. But if you read it out and look at it closely, what this does is it multiplies two numbers together and then prints them out to the screen. And it's not even this level of coding that we have to be comfortable with. And it's not so much that this is a programming language that we're used to, these very high level ones where you're allowed to think about things in terms of doubles or vectors or matrices, that you just say matrix times matrix equals third matrix, and all of that computation is done for you. We are probably decades away from having those kinds of libraries and that kind of high level languages put together for a quantum computer. So something on this level is what we're building towards slowly, but more realistically is a code like this, which is, again, it's a classical computing code that uses the MIPS formulation. And this is what you would actually pass to the machine to tell it to do something. And again, given that everyone was silent on the first one, I will not wait very long to find out if anyone can tell me what this does.
Sorry, is the main thrust these days actually coding a quantum computer, or to study, actually what the quantum computer might do by simulating it with classical computing?
So, depending on who you are, you can spend a lot of time working on like benchmarking the current machines, or you can spend time using the classical computer to do larger scale quantum simulations that are, noise free, to understand how algorithms and things work. But in either case, what you really most of the time are programming is things sort of at this level where you have to think qubit by qubit how you're going to have those two qubits interact, and you have to think instruction by instruction how those two qubits will be passed. And so I have had to write things very similar to this function right here, in fact, which is actually how you do the addition of two integers on a classical computer. So we are both for efficiency reasons and because these computers are so noisy and troubling, and because the libraries don't exist, like the level of experience you need to have with the very low level amounts of computing to make interesting things happen in the next probably 10-ish years is going to require us going very much back to the basics of computing.
I've seen assembly in my college classes, but I recognize some of the but I do hope I don't have to review it in order to get into
yeah. So I will say, like, you should at least be aware that this is the thing that the actual people programming them have to do. As long as you have a younger colleague that's willing to pick up a new programming language, it's not so difficult. But so that's part of what my day job is at the moment, is I have to think in that particular, like, explicit control over single qubits, even though I'm trying to imagine, like, what does a double or what does an integer look like on a quantum computer? So, what are the other things that you should at least be aware of, right? Because I just tried to tell you, you personally don't need to learn quantum assembly language all over again. So what you should be aware of is this idea of Solovay and Kitaev, which says that a universal quantum computation can be performed provided one has a set of 1 qubit operations that are sufficiently dense in SU2, where SU2 again is the group of unitary matrices with determinant 1. So that shouldn't be a totally crazy idea, that this would give you all of the possible operations that a single qubit can have acting on it. And you need, 1 multi-qubit gate, because if you don't have one multi-qubit gate, there's no way to introduce entanglement. So you sort of need a sufficiently dense 1 qubit set, so that you can do all of the possible things to give you whatever superposition you want. And you need 1, multi-qubit gate in order to give you entanglement. And so you maybe have heard of some of these or all of these gates, but depending on the hardware, depending on how you actually implement this thing at a fundamental experimental level, different types of manipulations on whatever your fundamental qubits are can be different, and it can be easier to implement some gates than others. But what's important for these universal digital quantum computers is that they have some set that actually will represent the full sufficiently dense SU2 plus 1 2-qubit gate. And their choices differ quite a bit, but provided you have at least that bare minimum, you can always write a code that will be able to be implemented on any of those computers, and it will run. Now, depending on how big those instruction sets are that they're going to have on these quantum computers, you can do things more efficiently or more quickly. And this is a big discussion, that theorists are somewhat getting involved in, is, well, of this large class of, easy to implement 1 qubit gates or easy to implement 2 qubit gates, what are the ones that are going to get us efficient simulations of hadronic physics or, high energy physics? So, but at a basic level, if you're doing, sort of circuit design as a theorist, most of the time you can sort of just use this particularly convenient set of universal gates, which is the C0 plus a Hadamard plus the phase gate plus the pi over 8 gate. And any quantum simulation you would like to construct can be built out of this set of 4. Now, it will not necessarily be the most efficient. It will not necessarily be the shortest. It will not necessarily map cleanly onto particular hardware, but it will always, give you a unitary that you want. And so, following after, Feynman's big point, Seth Lloyd in 1995 sort of showed that, provided that you have some Solovay-Kitaev, satisfying set of gates, any local quantum system can be correctly time evolved, and that it would be efficient, in fact, as opposed to a classical simulation, as we were sort of arguing before, will not be efficient regardless of what you do. But there's sort of, one caveat to that statement, which is that it's a quantum simulation, in the sense that as we always talk about, wave function collapse, complementarity, Copenhagen interpretation, all that stuff, it comes into play here at exactly this point, where you are going to be able to manipulate this quantum system however you want, but you're not going to be allowed to inquire what state it's in. And inquiring on what state it's in collapses it in some sense to some computational basis state of the quantum computer, and you'll no longer have superpositions, you'll no longer have entanglement. So unlike a classical computer where we can sort of debug as we go and look at each step and see how things evaluate, you're not allowed to do that on a quantum computer. You only get to look at it once, and that ends your calculation. So, what are the things that you should, really know, as opposed to sort of just being aware of in the background of how these things are going to work? Well, the first one is sort of this sort of discussion. So like, you should think about when people say gates and bits in terms of how many we have as sort of how many, machine level instructions we're allowed to give. And the bits and the qubits should be sort of thought as analogous to each other. So if you want to say, I would like to do, a 4 cubed lattice, I need at least 4 cubed bits times the number of degrees of freedom. And so that's a huge number to be asking for when all I have is 50-ish at the moment. But you should also remember that there's noise, and the noise is essentially the thing that drives these various different companies to say that they only have so many qubits and they only have so many gates, is that they are going to design a piece of hardware where they think that they can get the fidelity of these basic gates that we have to some certain fidelity, in the sense that if I operate on a quantum state with this particular gate, I will, somewhere between 95 and 99% sort of today, get the same answer that I asked for. And so sort of, again, unlike classical computing where you don't think all that much about, if I tell it to multiply 2 numbers together, it would give me the wrong number at the end. That's somewhat a niche case most of the time when we're thinking as theorists, but maybe as a computer science person you're more interested in. If you're doing real computations today on a quantum computer, every single gate operation you do has something like, a 90-ish% probability of being correct, but then a 10%-ish rate of being wrong. And so if you're, again, asking for 20 gates or asking for 100 gates or asking for 1,000 gates to be operated on, your likelihood of getting the right answer at the end is going to be very, very small. And this is sort of the key metric that has to be pushed up, is that until you can get higher fidelities, you don't want to build a bigger machine just because you won't be able to do anything with it. And you don't try and build deeper calculations because you'll just be swamped by noise immediately. So it's sort of tuning the noise to be as small as humanly possible is what drives both the choice of instructions and how many qubits people use and what actual length scale of calculations can be done. And as I sort of said, if you look at Google or anything like it, the state of the art is that we have sort of 10 qubits and you can do 10-ish gates. The long-term idea is that we will eventually be able to do error correction, which is this idea that you can build a logical qubit, which is a noiseless, perfect object that can be operated on from a collection of physical ones that are each in themselves somewhat noisy. And this can, in fact, be put on an even more rigorous foothold by saying what are called the threshold theorems, which is this idea that a particular model of quantum error correction is possible. And so by model, I mean, you decide which types of errors do you want to be tolerant to. Do you want to be tolerant to the fact that a qubit can flip itself? Do you want to be tolerant to the fact that you can have a phase rotation? Do you want to be tolerant to the fact that 2 qubits together could be doing some weird entangled bit flipping that causes errors? You choose, which types of errors you want to be insensitive to. You can define an error correcting code on top of that will fix those errors. And the threshold theorems tell you that for any given quantum error correction code, it will work, and you will be able to define sort of these logical fault tolerant qubits to those errors, provided that the fundamental gate errors are lower than some particular probability, which is entirely error correcting code dependent. And so a huge area of research in computational quantum computing science is, can we find codes that correct for as many of the errors as possible with as few physical qubits required to make a logical one, and with as high of these threshold errors as possible? Because if we only needed a 10% error to fully error correct everything and it only took 3 qubits, that's different than saying we need a 0.01 error rate and we need thousands of qubits to make one logical one. And so this is going to become this more pressing issue in the future as we try and move towards the fault tolerant era of quantum computing. And as was also discussed a little bit earlier, right now on my laptop, I almost every day will run 17 error-free qubit simulations, and I can do thousands of gates, and it only takes a few minutes. So in terms of the calculations I care about, we're very far away from having quantum advantage, because I can do very, very deep circuits with relatively large sizes of qubits. Now, I can't go much larger than this without devoting much, much larger classical resources, but there's lots of things you can tool around with just 17 qubits. The other thing you probably really should know is that connectivity matters. It's, again, you're not allowed to just think about integers or doubles or vectors or matrices. You have to have at least some vague awareness of the fundamental qubits you're going to be playing around with. And for example, here is Righetti's Aspen 8 computer that was just recently decommissioned. And you see that each of the qubits is numbered by a particular value, and that hopefully you can see the gray bars that match between them. And that tells you which qubits can be directly interacted with each other. So every single one of these qubits can be operated on with any single qubit gate, but only certain sets of qubits can be operated together in a 2-qubit gate. And so, if you have a problem, the way you lay down, the 16 qubits that make your 16-bit number on this thing will differ wildly in terms of how efficiently you can do computations on those 16 bits. And this is, sort of right at the edge of the things that I get involved in personally, as opposed to having more hardware-specific friends involved in. But it's this idea that, like, for example, I want to multiply 2 gauge elements together. So if I want to do quantum field theory, sort of one of the very fundamental things I need to be able to do is take 2 gauge group elements and multiply them. And for this particular discrete group that's called D4, there are 8 elements. So I can represent a given element of the group by an integer that goes from 0 to 7. And so if I want to multiply 2 of these integers together, I need 3 qubits for each of them. And so I need 6 total. And those are the 6 qubits that I've circled here. And hopefully you can see, if I had placed this almost anywhere else on this map, I would not be able to get those 6 qubits interacting as easily without having to swap around their values. For example, if you look at qubit 13, which is on this sort of second octagon looking thing, it's not actually connected to 14. There is no 14 qubit. So this guy is only able to communicate with 12, and it has a much different architecture around 13 than around 36, which is where this is built. Moreover, while each of these integers is represented by 3 qubits, those 3 qubits are not actually connected to each other. So in fact, 22, 36, and 30 represent one of my gauge elements, whereas 21, 35, and 37 are the other ones. So you don't even necessarily have all of your memory contiguous with itself if you want to do these things most efficiently. So just to hammer it home, like we have a deep understanding of, for many reasons, why quantum computers are going to be required for high energy physics. And there's sort of just one final one, which is that on a very firm, computational science perspective, there are a class of problems called bounded quantum polynomial. And this class of problems is known to be distinct from P, which is sort of the polynomially easily solvable classically things. It's known to be distinct from NP, which is sort of one of the more difficult area of algorithms that we talk about today classically. So some of our BQP problems, which are where a lot of high energy physics in real-time dynamics sits, either sit in NP or they even sit outside of that one in a much higher complexity class and being very, very difficult to solve classically. And so our computational science friends will tell us there are fundamentally problems that cannot efficiently be done classically. And to hope otherwise is to be, misguided. And it is my expectation that lots of the really interesting high energy physics problems we care about really do sit in these intractable classically regime. So on a quantum computer, as I sort of hinted at earlier, but I'm going to be really explicit, the more natural thing to formulate your problem in is in the Hamiltonian formulation. So while we sort of all know, again, from Feynman, that the difference between a Hamiltonian and an action isn't that profound in the sense that we know that there's a way to translate between the two of them, because of the way a quantum computer works, where you have a quantum state and you want to act on it with unitary operations, it's a lot more natural to construct things in terms of the Hamiltonian. Another important reason why we like the Hamiltonian formulation better most of the time is that it just takes fewer qubits. If you want to start computing things with the action, you need the full space-time volume, for example. You're doing a path integral over all d dimensions plus time. Whereas if you want to do something in the Hamiltonian formulation, you're just taking a single time slice and a single wave function at a fixed time. So you're only going to have to store the spatial lattice as opposed to the full space-time lattice. So you get 1 power of the length scale reduced. So it's just cheaper. But the bigger, more profound reason is that it's much more natural. Although people have talked about formulating the action formulation for quantum computers and how to solve certain problems with it. But most of the time people are thinking of the Hamiltonian. And so as high energy physicists, we're going to have to sort of relearn some of our, somewhat lost knowledge about how Hamiltonians work and the subtleties involved in them. So mostly as a setup for next time, what is the end of this talk and the rest of next Wednesday going to be about? So there's, again, if you're thinking about high energy physics, there's sort of two types of problems that you might want to get involved in. And one of them is the idea of quantum algorithms for big data. So the idea that there are algorithms and there are ways of solving problems that can be done much more efficiently on a quantum computer than classically, but they're not really a quantum mechanics problem in and of themselves. And sort of, the big examples people talk about is Grover's algorithm, which is this search algorithm that under specified conditions, you can do a search through a set of data more quickly on a quantum computer than a classical one. So you can imagine something like, a search engine like Google being able to do things more quickly. Or if you're trying to do data analysis on large, collider data sets, then potentially, you could get a speed up there if you're allowed to put that data onto the quantum computer. The other, big example of an algorithm that we know is faster is the quantum Fourier transform. So most of us are aware of, the discrete Fourier transform and the fast Fourier transform are these relatively optimized algorithms for Fourier transforming data on a classical computer. There is in fact an analogy on the quantum computer, and it's known to be faster. So if you can, for whatever reason, need to do Fourier transforms a lot, there is a way in which the quantum computer would be faster if you're sort of speed limited by that. The last one is what's called the HHL algorithm, which is a way of solving linear systems of equations or finding eigenvalues and things like that much more quickly on a quantum computer, provided you're sitting in the right structure of the Hamiltonian or the matrix you're trying to solve it for. So, any of your sort of linear algebra problems that you typically do on a classical computer, there are cases where those things would be faster. So, I've put some references here to people that talk about that stuff, and I've mentioned what they are, but most of what I'm going to talk about is sort of the fundamentally quantum mechanics things and the quantum field theory things. So doing real quantum simulations, things like nuclear structure and the actual dynamics of colliding hadronic systems like at the LHC. And now is maybe one of the more depressing slides I'm going to show you. So if I take what IBM and Honeywell says is some vague metric called the quantum volume, and I project out from what they say is their likely linear progression for the next 40 years, you get this blue line in the center. And then I've sort of plotted on it a few rough estimates of where interesting quantum field theory problems would sit. So they're sort of doing argon neutrino scattering is sort of at the bottom, that maybe we would start thinking about seriously in 2032. And then we start jumping up to 4-dimensional viscosities of discrete subgroup theories. So when I said at the beginning that I was hoping to see something interesting in my lifetime, I was not meaning the short term of my life. I was expecting to be around for at least 40 more years. And you can put error bands, which I aggressively put some blue ones on there that say it would move twice as fast or they would never improve again. And you really get a sense of how quickly this could change, either for the better or for the worse in terms of projecting when interesting things could happen. On the less pessimistic frontier, the SQMS Center that we've just started here at Fermilab with collaborators around the world is hoping to have a machine in the next 5 years that will be able to do lower dimensional theories for high energy physics and do sort of much, much simpler problems that are still of theoretical interest, but require still a hardware development that we don't have at the moment. But on the 5-year timescale, we're expecting these computers to get relatively better, that we can start trying some more quantum advantage level problems. As I've said multiple times, hadronic collisions really are going to require quantum advantage to do precisely, which maybe seems counterintuitive to a lot of you because we do LHC physics theory all the time. And the fact of the matter is, we've taken this larger problem, we've broken it down. So we use, factorization to give us PDFs and give us fragmentation functions and things like that. We of course, though, have to rely on this assumption that factorization is rigorous and that it's safe and that it's correct to use, which is not always true. And it also is only correct up to a certain order in alpha QED and electroweak. And if you try and push it beyond that, you're going to be getting new corrections that are harder to deal with without enumerating an increasingly large number of non-perturbative inputs. The showering that we actually do is based on using classical models of sort of billiard balls partitioning off themselves, or using something like KT algorithms, which have a small amount of quantum mechanical input, but doesn't fully track through the entire evolution, the true entanglement of all of your partons that are being showered out. And someday, if we were really, really optimistic, this could be replaced by one big quantum simulation. And what would it look like? It would look, as I said, basically just like a collision in a collider. You would write down an algorithm, and the entire point of this algorithm, the way that Jordan Lee and Preskel wrote it, is you basically, on your quantum computer, find a way to prepare two protons that are each given a momentum, and then you just time evolve them. And these two protons will then fall into each other, collide, and create a bunch of other particles, and then you let it time evolve longer so that the particles all move away from each other, and then you measure them at the end with something that is the exact analogy to a detector. So your entire physical intuition is exactly the same as what you have with a real collider. Now, of course, if you try and think about this large-scale algorithm, if you wanted to even try and estimate, how many qubits you might need for it, you'll find that you're already in the millions and billions of qubits to do something sensibly with all of your errors really under control. So this is far, far off. So there are cheaper things you can do, and one example of people both here at Fermilab and other places is this idea that instead of taking two particles that are well separated from each other and having them collide, why not just figure out what the response function of one complicated particle is to some external probe? So we're talking about how do we compute things like the PDF or the response function? And these things are complicated and non-perturbative and difficult in and of themselves. And so, thinking about Dune and places like that is where people were discussing how to do neutrino nucleon scattering. And it really is, just computing the response of this thing to being hit by some current. And, you can either extract it directly from the quantum computer, or you can get its Fourier transform and then just do that numerically after the fact. The state of the art is doing a triton where you've only included contact interactions. This takes 4 qubits. Again, it's this order of 10, C0 gates, and then about 10, 1 qubit gates to make it happen. It was done last year, and there were a lot of very aggressive error correction had to be done, or not error correction, but error mitigation, where they played with different noise levels and extrapolated away as much of the noise as they can, just to come up with something reliable for this very simple system of 4 qubits. And using that, they were sort of able to estimate that if you wanted a similar precision for this argon thing, you need something like 4,000 qubits and 10 to the 8 gates. So we're at least several orders of magnitude smaller from doing PP collisions and getting pions out, but that's still a lot. PDFs, as you can imagine, are almost exactly the same thing as the response function of the nuclei, except instead of thinking about needing to get nuclear physics correct in terms of the structure of that, what we're now going to be interested in is getting the parton or the protons physical preparation correct. So whereas the nucleons, their spatial extent is something like 10 Fermi, a single proton's PDF should only need you to have a single proton in the box, in which case you go from needing a 10 Fermi box down to something like a 1 Fermi box. So PDFs are sort of the very bare minimum of this sort of class of things where response functions are in terms of what you can expect to get for at least particle physics. So what does it take to actually get to something towards practical quantum supremacy or quantum advantage of quantum supremacy? Well, you can sort of figure out the math scaling if you think about it for a lattice field theory. And what you learn really quickly is that, what you're dominated by is the fact that you have length scales and resolutions that have to be taken care of. Or said alternatively, any calculation you're going to do is going to require some UV scale determined by, how far particles need to be separated or how big the dynamical range of this system is. And then you're going to have those are the IR scales. And then you're going to have some UV scale that determines how finely do I need to actually investigate this calculation? How precisely small in spatial extent or how high in momentum do I need to go in order to actually resolve the physics I care about? And hadron scattering, as I said, you need 2 well-separated protons, and you need to also be able to see proton substructure. Otherwise, you won't get any of these collisions happening. So you need very, very small resolutions with very, very large boxes. For the PDF, you only need sort of 1 proton, but you still need that proton resolution. And what I recently finally put out a paper on that has been discussed a lot is that things like transport coefficients or hydrodynamic modes are expected to be sort of quickly equilibrating values, and also don't require you to have something larger than sort of a thermodynamic limit of the box. And so you expect both the resolution and the length scale to be much closer to each other, and so require fewer resources. So I sort of have been arguing that viscosity is at least a near-term goal. It's interesting both from a theoretical point of view because they're hard to compute for all temperatures and densities and things, but we could also use them as an input into our heavy ion colliders and also into our neutron star dynamic simulations. It's also, as a theorist, interesting because we can test the KSS bound and see if we can find in these strongly interacting but far from conformal theories, how close to that bound we're actually capable of getting. Now, what this requires is, unlike preparing a proton, you need to be able to prepare some kind of thermal state. And you also need to define what actual operators are going to go on the quantum computer. And so this is the kind of thing that I do day to day is, how do I prepare the states I care about in terms of writing algorithms? And how do I actually formulate the problem of, a given non-perturbative operator calculation that needs to be done, and then mapping that onto qubits, or mapping that at least into the Hamiltonian formulation of quantum field theory. And as other smart people before me, including some maybe in this room, have written, there are these ideas that, in the same way that there are critical exponents for classical, or in the same way that there are critical exponents for sort of the static thermodynamic properties of theories around second order phase transitions, there are dynamical universality classes that exist. And so instead of having to simulate QCD to learn a lot about it, if you can find something that's in a similar universality class, but requires fewer computational resources, this can be a quick way to learn a lot more about QCD than what we can do in terms of having to wait until we have the resources for QCD. And I know I'm essentially out of time, so I will quickly say, on a completely unrelated note, that if you're interested in non-perturbative, quantum cosmology, this is really the place where all of the problems that require a quantum computer become obvious. And one really great example is if I want to imagine doing baryogenesis through a first order phase transition. So in order to make that happen, the first thing you need is you need to be doing quantum field theory in curved spacetime. And as this spacetime expands for whatever reason, whether it's the actual dynamics of the fields you have there, or you just couple it to some external field that's driving the expansion, like some classical inflaton field, it's actually this time dependence of the spacetime metric that's cooling off the theory. It's not that there's a lockstep change of the temperature with the time, but in fact, they have a feedback between the two of them that can become complicated. And you expect it to become complicated, especially maybe around a first order phase transition. So, first you need to implement, time-dependent quantum field theory in curved space. Then, you start worrying about these bubbles being produced, and you want to know, what are the, initial critical radii for these bubbles, and what is the distribution of eccentricities that actually come out of nucleated bubbles, as opposed to assuming they're purely spherical. What is the velocity that these bubbles hit when they start expanding through this plasma? What are their thicknesses of their walls? When you try and imagine this as a real, plasma, you should maybe be a little uncomfortable that we sort of are always assuming this relatively smooth fluid dynamics, as opposed to some highly complicated turbulent problem. And that would be something you could imagine trying to solve and thinking about, is that there are going to be a bunch of distributions on these properties that can affect dynamics in some way. Again, the generation of baryon number depends very sensitively on all these facts and how these collisions happen and how the exact shape of the bubbles are and what temperature, the inside and the outside. And then finally, after the collisions are sort of getting close to being over, there's still the dynamics of, the massive particles showering out and decaying as you finish off things. And so all of this, would in principle nicely fit under, you prepare a wave function at some fixed time and try and time evolve it. But the exact Hamiltonian you put in to make that happen is complicated. And then finding out how to measure each of these observables in a well-defined way is hard. People are working on it. They're taking baby steps. They're thinking about, doing the non-perturbative evolution of 1D theories, 1+1D theories in curved space. They're talking about, quantum inflation, where you explicitly have a true, pair of coupled scalar fields, where one of them is initially in some classical false vacuum, and you allow it to decay. But in that decay, because it's quantum mechanically actually coupled fully to another scalar field, you can do things like looking at how the reheating dynamics or how the preheating dynamics actually modifies the classical solution that you started with to actually give you the full quantum dynamics of the inflation. And then, you can even think about the really simple thing of just setting up, a Higgs field and studying how its false vacuum decay rate is in a fully non-perturbative way, whereas sort of, right now, the typical way we have to do it is you do, Coleman-Weinberg effective potentials, and then you try and do the matching between the two of them to estimate the rate. You can imagine doing something to all orders in the effective potential all at once. So I know I'm a couple minutes over, but I will conclude here just by saying there's a lot to do, and it's going to be an exciting probably 40 to 50 years of making this into a thing where we can learn a lot more about the fundamental properties of quantum field theory and the universe. It is certainly going to require some new intuition. It will, for at least the foreseeable future, require some of us to learn a lot more about the bare bones of programming, but that's part of what's going to make this an exciting field and make it possible. And there are lots and lots of things that I genuinely believe require these things, and I'm hoping to study some of them. And, on Wednesday, we're going to actually talk about what I do most of my day-to-day and talk about the actual theoretical issues that we can work on while we sort of use the machines and we wait for the machines to get larger, the problems that we as theorists really need to be tackling ourselves.
Let's thank Hank for a very interesting talk. We are a couple minutes over, but if anybody has urgent questions, we can ask them now before we take a break and come back for discussions. So if anybody has a question, go ahead.
I have a quick question if I could. At the very end, this perception or view that the phase transition is nucleation based as you were describing it, isn't there a view perhaps that it's a spiral decomposition a la Ginsburg-Landau, where you have a fast quench through and then a sort of a linear instability? So that's the question. This baryogenesis picture, is it accepted that it's nucleation, or is there a long wavelength linear instability type theory?
I would not be the right person to ask that precise question to. I would say this is one of the cartoon pictures for baryogenesis through a first order phase transition. And my perspective of what would be interesting here is that the reason we constructed this picture is partly that it's well motivated, as I understand, by like the actual effective potential and how it could happen in a particular theory where you'd have a first order transition, that it would go through a nucleation, at least for the potentials we have. But, part of the problem that I'm trying to solve with the quantum computer is that we constructed this picture partly because it was a way we could decompose the very complicated dynamics of a first order transition into pieces that are computable. And whether, something like a linear instability is actually there or something more complicated is exactly the kind of feature that's hard to do without the full, dynamic calculation.
Thank you.
Daniel, go ahead.
Hi, I wanted to ask about, I guess something that's kind of related to the universal quantum computer. So I think in your talk you stressed very heavily sort of, the importance of having a universal quantum computer with sort of a universal set of gates that people can just start to take and code on. But I don't know, at least in my mind, these sort of universal gates kind of just seem like a collection of transistors that you like, transistors and diodes and stuff. And but you would sort of never try to build a computer from scratch using just transistors. I mean, you have all of your operational amplifiers at least. Let's not even talk about sort of logic gate or all of the different fancy chips. But so are there other systems where people sort of I guess think of more useful not gates, but just like quantum operations you can physically do that would sort of take the place of something like, say, an operational amplifier?
Yeah, this is something that people do, and maybe I mean I can spin some more words and say that in the case of like the trapped ions, what their fundamental gates really correspond to is a set of laser pulses they can send in where they know the laser pulse will do a particular thing, right? So you can imagine or a combination of like laser pulses and magnetic fields. So if I take two trapped ions and I try and excite them both to the same excited state, I can use the same laser for that as long as they're basically not Doppler shifted from each other. I can excite them both. Or if I take a magnetic field that has some spatial dependence, instead I might split the states and then pulse only one of them with the laser. So like the actual thing that these hardware people do is they say, here are the set of like laser pulses and magnetic field manipulations I can do. I'm going to target particular collections of those that do some particular operation, which is sort of the same way you're saying like having the amplifier versus the transistors and things in the logic gates. Like they work really hard to find a universal set of gates for them that do what they want. And then if someone pushes them from the outside, they can say, okay, if you really, really need this particular operation, we can spend some time learning how to optimize our lasers and our magnetic fields to make that operation happen. So if you have some particular unitary operation you want, there are these sort of pulse control is sort of one of the big words that they talk about, which is that you're actually going to go in there and fundamentally control how the lasers and magnetic fields get manipulated to do whatever random unitary gate you might have wanted. And so people work on this thing where they try and design the machines to have more and more flexibility in which instructions they can do in that way. Is that sort of what your inquiry was about?
Yeah, I guess it just seems like if we had didn't just use like our these like set of 4 gates to try to do simulation, that like having sort of more physical. I mean, you're essentially setting up an experiment to test something. It seems like that sort of would be more useful for quantum simulation, I guess.
Yeah, so I mean, if you want to talk about things that get written into grant proposals, there is of course lots of this discussion of like the co-design of I as a quantum field theory, as we will talk about on Wednesday, there are some very, very specific operations that I know I'm going to need, and implementing them in terms of any set of the fundamental gates that I'm usually given by one of the companies is very, very inefficient. And I know from talking to people that do this that if I wanted to spend the time talking to them about doing pulse control and things like that, I could implement the exact two gauge element multiplication gate could be done at a fundamental level and probably done much, much more efficiently than if I wanted to, build it out of this universal set. And so there are some people that are working very, very hard to try and, cut down the time scale of getting interesting physics by trying to specially design every gate that they need instead of trying to build them out of the fundamental ones that they're given. And this is a huge, very, very open area of research. And it's also one where like part of what SQMS is we're supposed to be telling these hardware people like, the particular set of universal gates you're going to give me, I would prefer this set over this set because the things I care about can be more naturally implemented in those ones. Or can you give me, x86 instruction set instead of just giving me the bare minimum? Like these are the conversations that are going on now and will go on for the next very, very long time, I'm sure.
Okay, cool. Thank you.
Yeah.
Great. Let's thank Hank again, and I'll stop recording.